So probability density function will be denoted with small fx of x. Okay. So the density probability density function we also call it as PDF, probability density function. Whereas cumulative distribution function we call it as CDF. Okay. Probability density function we call it as PDF. How do we denote? We denote it as fx of x. Okay. So the probability density function is nothing but the derivative of distribution function. So fx of x is nothing but dfx of x by dx. Okay. So fx of x is called the density function of the random variable x. Okay. So if the derivative of fx of x exists, then fx small fx of x, that is whenever the derivative of cumulative distribution function exists, then the probability density function exists. Okay. There are some places where derivative of fx of x is not defined. Okay. So for example, if you take continuous random variable will have a continuous distribution function. No, this figure just now we have discussed. Continuous random variable will have continuous distribution function. So here at the corners, at these locations the derivative is not defined. Okay. So here because here the slope of the line will be changing suddenly. Okay. Because of that the derivative is not defined. Okay. So for that the density function will be defined as a step function. How do we define density function? Density function will be defined by a step type discontinuity here. Okay. So that is why whenever we have the continuous distribution function like this, what is the derivative of this will be the step function like this. Okay. And what is the area under this curve will be equal to 1. Okay. So what is the width of this curve here? The width of the curve is 12. No, 0 to 12 the width is 12, so that the height will be 1 by 12, so that the total area of this will be equal to 1. Okay. So whenever we have continuous distribution function at the abrupt change of the slope, how we define this density function? The density function will be defined by the step function like this. Okay. So similarly we have discussed that the distribution function will be having state step waveform for discrete random variable, yes or no? So in at the state step function, at every state step, what is that we use? We use the impulse function. We use the impulse function to denote the derivative of fx of x at the state step points. Okay. So the impulse function will be usually denoted by the formula here. What is the formula for impulse function? So if you want to find out the function value, for example, phi of x is any function which is continuous at x is equal to 0. Now if you want to find out what is the function value at x is equal to x naught, what you have to do? We have to integral minus infinity to infinity phi of x del of x minus x naught dx. This will give us what is the function value at x is equal to x naught. This is one of the properties of impulse function. So using this property, we can obtain the function value at x is equal to x naught by using this integration. Okay. So this is the property of impulse function. And we know that what is impulse function? Impulse function will have infinite amplitude. Okay. at at origin at zero duration. What is the duration will be 0, but amplitude will be infinity, so that what is the area will be equal to 1. So what is del of x? Del of x is denoted as it is having the area is equal to 1 at x is equal to 0. Okay. So we also know what is the relation between unit impulse and unit step function. The relation between unit impulse and step function is denoted like this. Del of x is equal to derivative of u of x. What is del of x is? Del of x is nothing but impulse function. What is u of x here? U of x is nothing but step function. So del of x is equal to du of x by dx. And it is also written like this: integral minus infinity to x del of psi d psi is equal to u of x. Okay, so the inverse relation will be denoted like this. So if impulse function is given, if you want to find out step function, we use this relation. What is the relation here? Integral minus infinity to x del of psi d psi is equal to u of x. Okay, so here, how do we use this impulse function to denote the discrete random variable? Here is, for example, cumulative distribution function is given as fx of x is equal to summation I is equal to 1 to n p of xi u of x minus xi. What is the density function? Density function is given as fx of x is equal to dfx of x by dx. Okay, so here p of x is constant, no, p of xi is constant. So the derivative will be applied to step signal. Just now we have discussed that the derivative of step signal is nothing but impulse signal. So here we will be getting impulse function del of x minus xi. So summation I is equal to 1 to n p of xi del of x minus xi will be getting for probability density function. Okay, so just now we have discussed this example. So we have discussed that this is the state step waveform we will be getting for distribution function. Okay, now if you find out the derivative of this, what happens? We will be getting at state steps, we will be getting the impulses. What is that? At -1, what is the amplitude is 0.1. At minus 0.1, 0.5, the amplitude is raised by 0.2. No, so here we'll be getting 0.2. So at 0.7, the amplitude is raised by 0.1. No, so at 0.7, what is the amplitude will be 0.1. At 1.5, the amplitude is raised by 0.4. So the amplitude will be 0.4. Like that, we will be getting the impulse function wherever we have the rise in step function. Okay, so this is the probability density function is derivative of distribution function. Okay, now we'll discuss the properties of density function. The first property says that probability density function will be a non-negative number. It is non-negative number. The second property says that the area under probability density function will be always unity. Okay, and the third property says that so the cumulative distribution function will be equal to what? Integral of density function. So capital Fx of x is distribution function. It is equal to integral minus infinity to x fx of psi d psi. And the fourth property says that the probability x1 less than x less than or equal to x2 is equal to integral x1 to x2 fx of x dx. Okay, so using this, these are the four properties of density function. Now we'll discuss what are the proofs. What is the first property? Fx of x is greater than or equal to 0. So we know that fx of x, the density function, is what? It is the derivative of distribution function. So it is d by dx of fx of x dx. Okay, and just now we have discussed that fx of x, the distribution function, is monotonically increasing. Okay, so that is why the derivative of fx of x is always positive. So what is small fx of x is non-negative. That is why small fx of x is negative. Just now we have discussed that the slope of distribution function is always positive. So if it is positive, what is that? The derivative will be non-negative number. So the density function is non-negative number. Okay. The second property says that integral minus infinity to plus infinity fx of x dx is equal to 1. Okay, so from this we know that what is a density function? Density function is derivative of distribution function. Now what we do integration on both sides of this equation. So we do integration from minus infinity to plus infinity fx of x dx, that is equal to integral minus infinity to plus infinity d by dx fx of x dx. So here dx will cancel, we will be getting dfx of x. So the integral of dfx of x is fx of x. Okay, now we substitute the limits minus infinity to plus infinity. So that is why we will be getting fx of infinity minus fx of minus infinity. So from the properties of distribution function, we know that fx of infinity value will be equal to 1, fx of minus infinity value is 0. So what is the value you get is 1. So integral minus infinity to plus infinity, fx of x dx value will be always 1. It means that the area under the density function will be always 1. Okay. So we know that what is density function is derivative of distribution function. Now what is distribution function will be integral of density function. So the distribution function fx of x can be written as integral minus infinity to x fx of v dv. Okay, so we know that from the definition, we know that what is fx of x? The density function will be the derivative of cumulative distribution function. So we integrate both sides of this equation. If we integrate both sides of this equation, we get integral minus infinity to x fx of x dx is equal to what? Integral minus infinity to x d by dx of fx of x. Okay, now fx of x dx. Okay, so from this we know that if you substitute the limits, we get fx of x minus fx of minus infinity. What is fx of minus infinity? Fx of minus infinity will be 0. So what is fx of x value will be integral minus infinity to x fx of x dx. This is the formula we use to obtain the cumulative distribution function from the density function. Okay, then the fourth property says that probability of x1 less than x less than or equal to x2, okay, will be equal to integral x1 to x2 fx of x dx. Okay, this is the property we have to prove. So from this property we know that probability of x1 less than x less than or equal to x2 will be equal to what? Fx of x2 minus fx of x1. So this particular equation we got from the properties of distribution function. Okay, so from this we get integral. So what is fx of x2? From the properties, from the what is fx of x2, here just now we have discussed, no, fx of x2 will be equal to integral minus infinity to x2 here, small fx of x dx. So it is integral minus infinity to x2 small fx of x dx minus integral minus infinity to x1 fx of x dx. Okay, now if you observe this figure, from this we can know, we know that x1 value will be always less than x2. X1 value will be always less than x2, no? So that is why integral minus infinity to x2 we divide into two parts, that is integral minus infinity to x1 and from x1 to x2. So integral minus infinity to x2 will be divided as integral minus infinity to x1 fx of x dx plus integral x1 to x2 fx of x dx minus integral minus infinity to x1 fx of x dx. So in this, these two will be same with the opposite sign, these two will get cancelled. So what will be left with? We left with integral minus infinity to minus integral x1 to x2 fx of x dx. So if you want to find out the probability between x1 and x2, we use this probability of x1 less than x less than or equal to x2 will be equal to integral x1 to x2 fx of x dx. So from this, if you want to check any function to be density function or not, we use the properties 1 and 2. So if properties 1 and 2 are valid or true, then we say that the given function is valid density function. What are the properties that fx of x value will be always greater than or equal to 0, then the area under, this is the property, fx of x value should be always greater than or equal to 0. And the second property is integral minus infinity to plus infinity, fx of x dx value should be equal to 1. If these two conditions are satisfied, then we say that the given function is valid density function.